To my talk on the deep time thermochronology of the Beartooth Mountains. I'm Chance Ronemus, and this work is co-authored with Devon Orme and William Guenthner. To get our bearings, the Beartooth Mountains are a mountain range in southern Montana and northern Wyoming, just north of Yellowstone National Park. This range is cored by Archean basement rock, which records a more than 2.5 billion year history of deformation, erosion, and burial. There's been a lot of geologic work done here. However, a lot of this previous work only captures snapshots of this history. New thermochronology methods can resolve much more extensive thermal histories ranging into the billion-year timescales. We're interested in using these methods to constrain an integrated time-temperature history of the Beartooth Mountains. To do so, we collected basement rock samples, shown here by the yellow symbols, from within the Beartooth range. We achieved good spatial coverage of the range. A lot of previous low-temperature thermochronology data had been limited to exposures near roads. We used multi-chronometer techniques, including the zircon uranium lead, biotite argon argon, and zircon helium systems to cover a range of temperatures and provide constraints on our thermal models. A quick refresher on the basics of geo and thermochronology. Both of these techniques use the radioactive decay of elements within crystals as a sort of geologic clock. In particular, in the zircon system, uranium decays to lead over a relatively long decay chain, which produces a lead isotope and 8 helium atoms. Lead comprises a large atom which can't easily escape the crystal lattice. Consequently, the zircon uranium lead geochronometer measures the crystallization age of rocks. Helium, by contrast, is a small atom that can more easily escape the lattice. Because of this, helium chronometers measure the cooling of the rock through some closure temperature, not its crystallization. Because we know that temperature varies with depth in the Earth's surface, we can use cooling through this closure temperature as a proxy for exhumation of the rock to the Earth's surface. Argon is somewhere in between, recording temperatures between about 300 and 425 degrees C. Zircon-helium deep time thermochronology formed the real meat of our study. This is because the closure temperature of zircon-helium varies with radiation damage to the crystal lattice. Specifically, at low levels of damage, the closure temperature increases. After a damage percolation threshold has been surpassed, it sharply decreases. This gives the zircon-helium system a broad temperature sensitivity, which we can exploit to model deep time thermal histories. Now into some results. Our uranium lead and argon argon analyses reveal that the Montana State High Point, Granite Peak, is comprised of 2.8 billion year old Archean gneiss. Additionally, biotite argon argon ages comprise two distinct populations, with Western samples yielding less than 1.8 billion year old ages, while those from further east yielded ages more than 2.2. These give us constraints on our thermal history that we model with our zircon-helium thermochronometer. The data from this thermochronometer is shown here. This is a zircon-helium date versus effective uranium, or EU plot, shown here. Effective uranium serves as a proxy for radiation damage to the lattice and is essentially the sum of uranium plus thorium times a constant. This gives us the potential that, for radioactive decay, which would have damaged the lattice and consequently resulted in a differential closure temperature. Because we can see that our higher EU grains record younger ages, it's likely that we have surpassed that threshold and are now seeing lower closure temperatures in these highly damaged grains. A well-defined date EU correlation is essential for deep time thermal modeling with this technique. Additionally, there's not a strong correlation with any other variable examined here with zircon-helium date. This suggests that these samples, even though they're from a large swath of the Beartooth range, likely share a broadly similar time temperature history. This is ideal for thermal modeling of this data set. We conduct a series of forward models to test the sensitivity of the predicted date EU trend to major thermal events in the past. In this technique, we plug in a hypothetical time temperature history that the rocks would have experienced, and then we generate a predicted date EU correlation shown here. We examine the fit of the predicted date EU correlation to our observed data. This allows us to see that the Proterozoic history has pronounced effects on damage accumulation, affecting the closure temperature of zircon grains and consequently their date EU correlation. This suggests that our data set is indeed sensitive to the Proterozoic history. In this case, of the scenarios examined here, 2, the purple path corresponding to this date EU envelope, gives the best fit. We then inverse modeled our data set. In this technique, we used a Monte Carlo search algorithm, which tries a large number, in this case, a cumulative 100,000 paths, time temperature histories that intersect previously defined constraint boxes. They then compare the predicted zircon-helium cooling temperatures to observed inputs. In this case, we combine many grains from our data set into 7 synthetic grains because the model can only take 7 grains as input. We found 22 good fits. We then forward modeled the best fit paths shown here in black from both our upper and our lower elevation sample groups. They both form pretty good fits to our observed data. However, these sample groups make mutually exclusive predictions for the timing of major thermal events, which can't have been the case considering they were sampled only kilometers from one another. In order to explore if they predict possible shared thermal histories, we overlay the envelopes of good fits here. These good fit envelopes do indeed overlap. We then iteratively forward modeled within or slightly outside this good fit envelope and compared the predicted data U correlation of these forward models to our data set, as well as existing low temperature thermochronology data such as appetite fission track. Some takeaways from our study. Our argon-argon results have implications for big sky orogeny tectonism. This Paleoproterozoic tectonothermal event was likely associated with the collision between the Wyoming craton, in which the Beartooths are located, and some Archean terrain out to the west. The thermal overprint of this event has long been recognized in locations west of this feature known as Giletti's Line. However, our results indicate it perhaps extended as far east as the central Beartooths. Additionally, our results allow us to affect potential timing of the formation of the Great Unconformity, a surface across which about more than 2 billion years of geologic time is missing from the stratigraphic records in the Beartooth range. There's been several studies now from Western Laurentia looking into this, and they all agree pretty well on initiation of pre-Great Unconformity erosion around 1 to 0.8 billion years ago. This could have perhaps been associated with the assembly of supercontinent Rodinia. Additionally, our best fit time temperature scenarios indicate cooling from late Pennsylvanian to Jurassic time, which is broadly out of sync with nearby areas. However, some existing evidence showing deflection of paleocurrents and a preserved appetite fission track partial annealing zone may suggest this is possible. Perhaps these rocks were feeling the far-field effects of tectonic events such as the ancestral Rocky Mountains. Our results also indicate rapid uplift in late Cretaceous to Paleogene time, which is broadly consistent with previous results from low temperature chronology, as well as retrodeformation of cross sections. This age is somewhat younger from recent evidence from southwestern Montana and Idaho. Conclusions from this work are that zircon-helium thermochronology can indeed deconvolve complex billion-year thermal histories. We recommend that this technique be paired with other thermochronometers and independent geologic evidence such as stratigraphic and structural data, as well as forward modeling. Ultimately, the Beartooths experienced a protracted thermal history, which was likely intimately linked to both geodynamic processes of Earth's lithosphere and mantle. Thank you.